Good morning and welcome to lecture 14 of Quantum Physics for Non-Physicists. And today is the 29th of October. And we'll continue what we started last day with stationary states in 1D. This is still chapter 15 of the Schumacher Westmoreland book. And today we'll do one case of the scattering barrier. And to explain what we're going to do, I have a very nice analogy. So this is from a book by Robert Heinlein called The Cat Who Walks Through Walls. So inside this book, it's a wacky solipsist sci-fi book, but inside it, there's a story of this cat where, of course, it's impossible to walk through walls, but this cat was so young that he didn't know it was impossible, so he just did it, and they crossed through walls. And then this cat goes along with them in many adventures. So what we'll see today is again the case of like a wall, a quantum wall, and how quantum particles that should not be able to go through this wall because they don't have enough energy, they still will manage to go past the wall. Okay, with some reflection, but they'll still go through the wall. And this is the phenomenon of quantum tunneling that we'll see today. And just think of the kitten walking through walls. So before we get started, let's just recap what we did last time. So we finally started looking at non-zero potentials. So Hamiltonian has a kinetic part and then a potential energy part. And then we just wrote the wave function Schrodinger equation like this for stationary states, because we know that the evolution of any state can be expressed in terms of the evolution of the stationary states, which just get a phase. Good. And then we saw that the general way to do it is to take our physical space, break it into patches that have like similar behavior of the potential, and then just find the solutions for each individual part, and then glue them together. And to glue them together, we can use some tricks. So some are these continuity conditions, which say that the wave function must be continuous. The derivative is also continuous if the potential is finite. And the second derivative is also continuous if the potential is continuous. So not in cases like these sharp edges, but otherwise in more physical cases. Good. And we also saw that, well, the wave function should be normalized, so it should not diverge to infinity. And we saw that the energy of the particle must be higher than the minimum of this potential. So here could be something there. Okay. And then we looked in particular at the special type of easy settings where there's just flat potentials on the left and on the right, and then there'll be some area with some interactions on. Something strange can happen. Very good. And then we found the solutions for the flat regions. So if the energy, for example, here on the left, if the energy is higher than the potential, then you get this oscillating waves with the momentum being given by this thing, depends on the mass and depends on the difference between the energy and the potential. And if we're like in this region, this is the average energy, and the potential is higher than the energy, then this wave function wants to decay. What we get is some exponentials. And so one would go down, one go up, and then you see it, what happens at infinity, and you see that some of this will not be allowed. Okay, and again, this exponent will depend on exactly the same thing, so the difference between the potential and the energy, and the mass of the particle. Good. We saw three different types. So we saw reflecting state, so this was when exactly what I told you now. So when on the left, for example, it could be on the right, but on the left, the energy is higher than the potential, and on the right, the potential is higher. So then on the left, you have the superposition of an incoming and reflected wave. So waves with the momentum there and there. This is just a solution to the differential equation. And on the right, you have some decaying exponential, because again, the other term that would go up is not allowed because it's not normalizable, and something in between. Then we have the scattering state, and we saw that it can be seen as a superposition of something that comes from the left and gets partially reflected, partially transmitted, and the other way around. So partially tuck and partially there. Okay, so this in particular is something like this, where on the right there's only one wave going. This is one solution to the differential equation, where we just put the d equals 0. And another solution was is to reflect everything. And because the applications of this kind of settings are, we shoot electrons at something funny in the middle, and we compute, I don't know, the transmission coefficient. So how much of what's the intensity of the wave function on the other side, or the amplitude of the wave function on the other side. Then we care about problems of this sort and not so much about the ones where we have particles coming from both sides. But of course, this will depend on the application. So for now, we can worry about this kind of problems. And the other one we saw was bound state. So this is when on both sides the potential is higher than the average energy. So the wave function must decay on both sides, and then depending on the shape of what's happening here, actually only some values for energy will be allowed. I did not explain this last time, but we'll see an example. I think in the next lecture, maybe if you have time, this lecture. Okay, so those are the 3 possible cases for what's happening on the left and on the right. And then we started looking at options for what's happening in the middle. So the first one was just unphysical, but it was just this step potential, right? This is what we saw last time. And in this case, if we have the reflecting case, meaning that the average energy is lower than the potential on the right, then indeed what we have is something that decays on the right and decays exponentially on the right. And you have this incoming and reflected wave. In the scattering case, again, you have a superposition of this case and the other case. But we saw by gluing all these conditions together, the coefficients for B and C, and we saw again, so we have incoming wave, reflected wave, transmitted wave. Okay. What's an example of something like this? Well, it could be like you're shooting a particle at some substance, and the substance just acts as like a flat potential. Okay, or you're shooting it at some kind of field that just acts like this. So where the particle does not discern like different atoms in the substance, for example. Okay, then just by measuring like what's the intensity of the flux of particles that's arriving here, if you shoot many of them, of course, then you can determine things like, oh, what's the height of this potential, right? Okay. So today we're going to look at another case. So this is the square barrier, like we saw before. So we have that the potential is 0 everywhere except in a region between 0 and L where it's some V0. And again, we're going to look at 2 cases where the average energy is below this potential and when it's above. In both cases, we get to see very funny quantum effects that you would not expect to appear if you had classical intuitions. Okay, so the first one, spoilers, what we'll see at the end is a phenomenon called tunneling. And this is when V0 is larger than E. So let me just copy the picture again. And let's again consider the case of a wave coming from the left. And I'll just write here I'll just make a drawing of what the solution will be. It will be something like this. Something is going to get reflected. It's going to decay, and then you're going to have something on this side. Okay. So what are the continuity conditions? So as we saw, f of x must be continuous, and the first derivative in order to x must also be continuous because the potential is finite. What's the general form of a solution? F of x equals eikx. So in principle, I could put an a here, but because we have this normalization condition, this already gives us one of the constants. So I just get rid of this one here. So in the middle, we know that we have some exponential decay, bx plus dx. This is from L. And after, again, now here we're only considering the case where it's going to the right. We use F because E is already used for energy. Okay, X. If X is larger than L. Okay. What were K and B? We can just take them from the general solution again. So this was 2 mu E over h bar square. And here we get 2 mu over h bar square is 0 minus E. Okay. So now we're going to see the continuity conditions. And now we have two zones that are critical at x equals 0. The wave function on the left must equal the wave function on the right, and the first derivative as well, and the same at x equals L. So this is just the general way to solve problems. We'll just apply it here. We'll skip some steps later on, but let's see. So at x equals 0, what we have? So f of x at x equals 0 being continuous. We just take here. So this means this must be the same as this when we replace x by 0. So all the exponentials are just 1, right? Because x is 0. So you get 1 plus b equals c plus d. And the fact that the first derivative is continuous. Oh, that the first derivative is continuous. Well, we go back. The derivative of this is just putting the ik there and the same there, minus ik, and here put b there and minus b. Okay. And then we replace again the x with 0 in the exponents. So we get is ik 1, here would be ik 0, so this is 1. Okay, that's what I'm doing in general. So I'll minus b because it's e minus ik. Okay, I'll just omit these things in general. Equals, so here we get b c minus d. Okay, by the same method. Okay. And at x equals L, we do the same thing. So now we need to have this being the same as that. Okay, we can do this. So we get C EBL plus D E minus BL equals F EIKL. And the fact that this one is continuous, we get B CEBL minus D equals IKF EIKL. Now, this might look a bit horrible, but look, the only variables are B, C, D, B, C, D, and F. Okay, there's some exponentials here, but we can think of them as constants. What we have is 4 equations for 4 variables. Okay, so this is something one can solve with linear algebra. 4 linear equations, 4 variables. Okay, so we can determine all of them. So we can determine B, C, D, and F as functions of what? Well, they're functions of B, K, and L, but B, K, and L did, well, of L. And then we have V0 and E, right? And mu. These are all the things that are needed to determine K, to determine B, and therefore to determine everything. Good. I will not show the results for all of them. If you can see, they are in the book, but because it's really just solving this linear system of equations, it's a bit tedious. And we're only interested in some things that give us some kind of physical insight. But I can show you just to give an idea of the aspect of it. So F looks like this, and don't worry, I will not ask you to solve these things in the exam. E minus I K L. What's important is that you know that in principle you'd know how to do it. Minus, and here's B minus K squared. There might be typos, but it's something like this, right? It doesn't look too pretty. And F, remember, F is what's is the coefficient of the thing that's transmitted on this side. Okay, so this is not very pretty, but we're interested in some things which I will maybe in the next lecture justify a bit more why, what's the physical significance of this, or we'll have an exercise with this. But if we think of the transmission rate, so this is kind of the intensity of the wave that is transmitted versus the incoming one. But A, we saw A was 0, right? Sorry, A was 1, we determined it. Up. We put it, no, there, exactly. We put here that A equals 1. Okay, so this is really how much of it goes through compared to how much came in. Okay, and of course it's a square because the probability of finding a particle there will depend on the square of the wave function, well, modulus square of the wave function. Okay, and again, the reason why we are plotting this thing in particular is because we know that it will give us interesting results, right? Because people have tested this, and there's something we can do experimentally that's quite cool with this. So we get 1 plus V0 square for E V0 minus E, and we get the hyperbolic sine square of BL. And don't worry too much about the exact form. Let's just plot it. So if here's BL, what does sin H square of BL look like? If here's 1 and here's 1, it looks like something like this. Very symmetric. Okay, so it goes up in a monotonic way is the thing that matters here. Okay, and now we're going to look at a few special cases to get to try to get some intuition for how T behaves. And you'll see that it will be justified by the result. Yeah. So let's see if BL is smaller than 1. This is kind of what we can call the very narrow barrier limit. Then means we are like here in this region, right? Which means that this sign is going to be close to 0, which means that this thing is going to disappear and T is going to be more or less 1. Okay, so in this case, and again, this is a very, very gross approximation. We could go and compute the exact thing. But T equals 1, which means that in the case of a narrow barrier, almost all the wave gets transmitted to the other side. Okay, so this is like the cut that really goes through the wall. In the case of a larger barrier, then we can just do the asymptotic behavior of this function here and plug everything together. And I will not subject you to that, but I can show the result. Well, T will grow more or less like some constant. And here, E minus 2BL. Okay, this is a 2. Maybe I should just do it again. 2BL. Which means that it decreases exponentially with B and with L. So what is BL? Let's try to get some idea of the orders of magnitude of things here. So what was B? B was just this constant, which I'll write here in a different way. Square root of mu. Here's square root of V0 minus E. And here L. And now let me just give you an idea of the orders of magnitudes of this thing. So for H bar is very small. This is tiny. It's kind of order of 10 to minus 34. This, I mean, as soon as the mass is large, then BL is going to be larger. And then we see that the transmission coefficient will decrease exponentially with B, so in particular with the mass. Okay, so this means if you have a very large cat, it cannot go through the wall. Only very small cats go, which is why we don't see quantum tunneling when you throw a ball at the wall, for example. Right? So this, for example, in the case of the electron, mu is kind of the order of 10 to minus 30. Okay, what are typical energies for like quantum particles going? You can think of one electron volt. This is a typical unit used there. And maybe later we'll get into the significance of this, maybe not, but just to give you some idea of minus 19. And then if you plug these things together, so remember that here you have the square root of this, so you get maybe minus 15, minus 34, minus 19. It gives you an idea of how wide this barrier can be so that you still see any tunneling, and it needs to be very, very small. Okay. So our goal is going to be to plot if we have here the energy of the particle, where at some point is going to hit V0, what is the transmission coefficient coefficient, right? So how much of it gets transmitted. And what we did now was this region here, when E is smaller than V0. And we saw that, you know, for barriers that are not too narrow, then it will go down exponentially on BL, so in particular on the energy. Okay, so it will go like this. And now we want to see what happens in this area. So we need to see the case of energy larger than V0, and the result is actually quite surprising. So, in fact, I can write already what the result is going to be. So the second case is going to be resonant scattering. And it has quite cool applications. So this is the case V0 is smaller than the energy of the particle. So let's get our drawing again of the barrier. Now we'll have E to be somewhere here. And we know that we'll have some incoming wave with some, let me try to do it more properly. I'll just do it down here. Some incoming wave. Here again, we consider the case where there's only an outcoming one. So incoming, reflected, transmitted. And in the middle, we know that it's also going to be, because the energy is higher, it's also going to be a wave, but it will have a different period, right? It will have a different K. Okay, so I'll put it there. So more specifically, phi of x is going to be e to y kx plus bi minus I kx if x is smaller than 0. Now here we have c. Now we have an I here because the energy is still larger, so we just have a different k prime plus d e minus I k prime x. And here we have f kx. Again, the other solution is also possible, but we'll look at the ones like this, where now we have k is the same thing as before, 2 mu e over h bar squared, and k prime is 2 mu e minus v0 over h bar squared. Good. So again, now we look at these normalization conditions at x equals 0. Let's see. So we want this to be continuous, the wave function to be continuous. What we get again 1 plus b equals c plus d. But now if we look at the first derivative, then what we get here, we get ik 1 minus b equals ik prime c minus d. And the i's cancel out. Good. And again, at x equals L, if you look at the wave function continuity condition, what we get, C E I K prime L plus D I K prime L plus F E I K L. And here we get IK C E I K prime L minus, oh, this was a D. D minus I K prime L equals, this was K prime, I K F E I K L. Okay, so the big difference to the other case is that all the i's cancelled out. Yeah. So if you see here, in this case, we had some imaginary part on one side and on the other, and this is what in the end gave us here the hyperbolic sign. And here everything is real. So the function that you're going to get at the end, so you can solve it in your own time if you want to do it. If we look now at the transmission coefficient, it's going to be m squared because a is 1. Then we get, again, that 1 over t is going to be the same thing. But now here we have sine squared of k prime L. Okay. And this is a very different animal to what we had before, because if you plot here the sine squared of k prime L to k prime L, then this looks more like right where this is 1. Okay, that's nice. That's very, very different. So what is the behavior now? Well, if you have the narrow barrier, if k prime L is smaller than 1, so this narrow barrier, then like before, you know, we are in this region, this is going to be very small. You can say this is almost 0, so t is almost 1. Perfect. Okay, which makes sense, right? If when the particle was smaller than, when the energy of the particle was smaller than the barrier, it could still pass through. For a narrow barrier, now that it has more energy, it will still pass through. Okay. What about when KL is larger than 1? Well, then we have this interesting condition, because this sign is going to be periodically 0. And whenever this is 0, then this term goes away, and t is going to be 1. Okay, so this means, and when is this? When is it 0? Well, it's 0 when we have here pi, 2 pi, 3 pi, etc., because it's the square of the sine function. Right. So then what we have is, if k prime equals n pi for a natural number, well, more than a natural number for any integer, but in this case it will only be natural numbers, then t is more or less 1. And what does this correspond to? So k prime, remember, is kind of the, it's the momentum of the particle while it's inside this barrier, right, while we're going through the barrier. So this corresponds to a solution inside here that is very similar to what we saw for the particle in a box, like 2 classes ago. So this is n equals 1. It means that it's going to look like this. N equals 2, it means it's going to look like that. N equals 3 is going to look tuk, tuk, tuk. Or we can tuk, 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 tuk. Okay, that's no longer beautiful, but it's this kind of solutions, right? This is n equals 1, n equals 2, n equals 3. Okay, so this tells us that for energies such that the momentum inside the box is gives us this half slope period, then we have a very high transmission rate. And let's just replace what K prime L is. So remember K prime L. This was let's do it like we did before, square root of 2 h squared, square root of mu e minus v0 L, and we want this to be n pi, right? But this gives us a condition for e minus v0. So just place everything on the other side to get h bar square pi square 2 mu L squared, and here n squared. Okay, let's call this thing here like E1, for example. Yeah, why not E1? It's not easy, just yeah. So these are exactly kind of the solutions for the particle in the box, except that now the only difference is that instead of the energy being given by energy times n square, is a shifted version of the energy shifted by this potential. So now let's try to finish this plot that we had. Now let's finish it there. So this was the tunneling part. And now the scattering part, let's say that the maximum of the potential is 1. This is the maximum. And the way this is going to behave is that it's going to get very close to 1. At what intervals? Well, at intervals that are some energy 1 times n squared. So they're going to get farther and farther apart. But also as the energy grows, this term here becomes larger, right? So this becomes larger, this becomes larger, which means that overall we're going to tend to go to 1 in the transmission rate, because this whole thing is going to go to 0. So it's going to anyway start getting quadratically larger, and then modulated by this sign. So it's going to look something like this. Let's see if I can draw it. Oop. Here's the first resonance. Then it goes down a bit. First resonance. No, I want it to go down more so that you can see the difference later on. Second resonance a bit farther away. Now it doesn't go down as much. Third resonance, much farther away, and so on. Okay. We use the term resonance because it's exactly the same phenomena as like the resonance in the box of a guitar, for example. The shape is such that when the wave functions have the right period, have the right wavelength, then the sound is amplified, right? It's the same idea here. So when the wave function inside the box, inside the barrier has exactly the right wavelength, then it gets transmitted much, much more. Okay, so these are called the resonance peaks. Okay, also that. Okay, and this is tunneling. Okay, so what are some applications of this? The most obvious one is to metrology. So suppose that you can control the energy of the particle. For example, you have something that can shoot electrons at different energies because it can modulate the electric potential inside this cannon, and then it will shoot electrons at different energies, right? And we want to, you don't know how high a barrier is or how wide it is, right? So then you just start shooting the electrons at different at these different energies, and at some point you'll see that many more get transmitted on the other side, and again and again and again. And this gives you already this energy delta between the resonance peaks, which you can use then to work out, depending on what you know, well, yeah, to work out L, right? So then you can use this to measure, for example, how thick some material is, if you can approximate the potential like this. Reversely, you can use it if you know the mass, but you don't know the energy, and you can extend how wide this potential is, then you can use it the other way too. So we just shift V, or we just shift L. And again, if you get the resonance peaks, then you can guess the energy of your particle. So this would be, instead of plotting to E, you'd plot here to L, and you get a similar plot, and then you see this. Good. So these are some of the like real world applications of this very, very basic idealized scenario. And in the next lecture, I know that you did the finite well, so this is going to be the opposite case where you have a box, but a finite one, and we'll quickly recap it, and then hopefully we can start already with the new part of the lecture. Okay, thank you, and we'll stop here.